full-time at a university so that I'm not in the process of applying to 12 universities and also trying to get my own funding, right?
God.
But,
yeah.
But in your spare time,
I'm working on developing a weather and climate lab class as a gen ed, with very simple hands-on experiments that you can do to kind of demonstrate some of the basics of weather and climate. And you can do a CO2, oh hey, more CO2 in the atmosphere, therefore warmer. You can do that in your kitchen.
Sure.
You need a mason jar,
of course.
baking soda and vinegar, right, and a thermometer. And so I'm working on that curriculum, but I really like that as hands-on. And once I get that curriculum, I want to test it out and produce it as a course on my YouTube channel. But yeah, that's after I get this proposal out for my actual job that pays me money.
So you've done something on climate stuff with some of the indigenous Hawaiians on the Big Island. And one of the phenomena on the Big Island is you can set your watch by when rain starts, right?
Yeah.
3:45. I mean, it is that good.
That is the beauty of Hadley circulation.
Hey, welcome to Debate Hub, everybody. I am Chesh, your master debater, and we are here for Volcano Watch, our monthly show where we track Madam Pele, where she's been dancing and exploding recently. But you'll notice there's no Maanyaa here today. We are definitively a number of shades lighter at this time.
Sorry, I'm so pale.
But we do have Dr. Maddie with us today. I will get her to introduce herself in a second. The reason Maanyaa is not here is because she has internet outage for the day, and I had to do some time math to figure out whether or not she was actually going to be here. So if she swings by, we'll let her in, but if not, too bad, she's missing out. We've got Landon with us, but Dr. Maddie, who are you, and what is it you say you do?
Oh, hey team, hi, I'm Dr. Maddie. You can find me on the internet, where I do some science communication and pseudoscience debunking over at Science Side Up. And you can find me doing tabletop role-playing content over on OK Roll. I'm more active on OK Roll right now. We're trying to build that one up. And what I am, I'm a doctor. I'm still getting used to that. I got my PhD about a year ago. I have a PhD in meteorology. I'm a real doctor now, just not a very useful one. I have my PhD in meteorology from the University of
That's all
Oklahoma.
entirely relative.
Yeah, that's true. I know we're at Volcano Watch, but I'm wearing my Tornado Watch shirt.
Yes.
Which I feel really good about. It's not tornado season, don't worry. And right now I'm a postdoc research associate. Doing research is my job. That's what I do. Which means I sit at a computer and I edit Fortran code.
Oh boy.
Because Fortran is still what we use in atmospheric science, because nobody's learned.
And it's physicist Fortran code, which makes it all the more special.
Yeah, it's what I'm doing right now is large eddy simulations, and I'm making them have clouds. That's what I'm doing.
I'm sure having a doctorate about the climate is not relative to what's happening on the planet right now whatsoever. Landon, how are you? What are you up to?
I'm doing fine. I'm having a good time doing a lot of coding with regards to getting ready for the 29th International Obfuscated Sequel Contest, which we hope to open in December. So there's lots of code stuff there. I'm looking at technical sanity and insanity with regards to AI technology. And I'm also doing various astronomy bits. I am a planetary scientist, and so is Dr. Maddie, but she specializes in a very critical part of planets called atmospheres, right? It makes our Earth fail to suck because most of the universe sucks as far as atmospheres go.
It's true.
Isn't it mostly a vacuum? Isn't that? Am I out of the? Was that the joke, or am I just out of the loop here?
No, listen, it's really easy to forecast the weather on, say, Mars, right? Because its atmosphere is effectively all CO2 and only 1/100th the density of Earth's, right? Yeah. So, man, I can tell you what the weather on Mars is anywhere. Earth has the absolute audacity, right? To have water in its atmosphere that can exist in all three states of matter.
Yeah.
And
Sure.
How dare?
yeah, how dare, right?
It has that, but on the other hand, if you look at the weather on Jupiter, right?
Ooh.
Because Earth is just a surface thing, but Jupiter's got thickness, right?
Jupiter's got thickness and Jupiter spins so much faster
It-
that you have significantly more defined bands, which also means that like storms last longer and the composition is different. So yeah, Jupiter's really crazy. Jupiter has more like so much energy in it because of how fast Jupiter is spinning. I don't know enough about the composition of Jupiter to understand like the full vertical profile of what's going on, or chemically what's going on. But yeah,
Neither do astronomers, but we're learning.
I guess we're gonna have to do another show sometime. That is the atmosphere of the planets or atmospheres in the solar system, because I think that would be really interesting.
And I don't know if Landon knows this. Landon, do you know my undergraduate I double majored in math and planetary science, and I did all of my undergraduate research on Lola with Marie Zuber. That was really fun.
So I know you guys had something you wanted to discuss before we got into Kilauea and before we moved our little butts into Hawaii. So please.
Should I do a screen share thing and see if commits screen sharing?
Yeah. If you're ready, are you sure? Did you make sure you closed all your porn tabs?
Well, we have volcano porn.
Oh, so you didn't? You in fact opened your prawn tabs for today. I see.
It's an expression basically. We got lava bits. So Dr. Maddie, one of the things that we do commonly at the beginning is we talk about the fact that volcanoes are a very common thing. To say a volcano is erupting is like saying it's raining someplace on Earth. This particular database is updated every couple of months, but back in August there were 47 erupting volcanoes. In this year, the eruption count is at 56. Last year, about 65. And the average number of eruptions is around 79. So, but of course, eruption is a sort of a vague term.
I was actually, that was my first question was, can you please define eruption for me?
And insert debate about semantics here.
No, listen, it's not a debate about semantics. It drives people insane. But when you're doing science, right, like you have to be very specific about your terms, in order, because to make sure we're talking about the same thing. This drives my husband, the lawyer, insane. Because I'll be like, that's not what that word means. And he'll be like, yes, it is. And I'm like, not in science. That's not what that word means.
No. If it makes you feel any better, I recently had some contention in court because of the word I used, because I use different terms sometimes when I'm live because I'm talking to science people versus, speaking colloquially.
Yeah.
And, the notion of...
It's not related to my mug at all.
You have an active volcano, and is it erupting... And then does it have, but they'll say, does it have lava visible? And then is lava coming out? Those are various degrees of how much it is going. So we use this as a big thing. But for Rob, so there's a database showing the red here is where it's quite active, right? There is a ongoing eruption with significant outgassing and lava. And if we look at who the active volcanoes are in terms of red, Italy, Stromboli, and Etna are always in continuous eruption. And Stromboli is known as the lighthouse of the Mediterranean, and it just is always sort of there. And Etna is pretty much having stuff coming out or just about ready to come out. Iceland, this time, we do have a thing on the Reykjavik Peninsula that is actually erupting right now, so it went back there. In Africa, we have, of course, the thing of the African continent being ripped in pieces.
I thought you meant ripped like muscle.
Yeah, well, it is rifting. It is going to be coming to pieces, and as a result, we have a pair of volcanoes that are always going to continuous eruption in DR Congo, and of course there's the area up in northern Ethiopia, which has sort of a continuous eruption set that's really nice. Indonesia usually leads the pack with this time 8 active and erupting volcanoes. This particular one is particularly thing because it's actually currently a very aggressive volcano, so it's actually even redder than red. If we look at who else is on the list, of course, there's nothing actively erupting for some value of active in North America. America, you have the one in
no Canada
Central
volcanoes.
Mexico is always there, and of course, if you want to see the thing about volcanoes in Canada, check out this show I just did on with Dapper's channel.
I'll put a link to it in the chat.
So yeah, Central Mexico has 1, Guatemala has 2, Nicaragua, Costa Rica has there. In South America, Ecuador typically has 2 erupting right now. There's the Cacahu, which is on the Chile and Argentinian border. That's erupting, and so is Peru. So they have South Atlantic Islands has been in an eruption for quite some long time. One of the ones that's always in eruption is Mount Erebus in Antarctica. Yes, there are volcanoes in Antarctica, and it actually has the world's largest lava lake, active lava lake, although it is a bit of a chore. Pacific Ocean, of course, Hawaii is erupting, although right now it's not shooting out lava, but it's in eruption, so that's a thing. Papua and Santa Cruz Islands and Tonga and Vanuatu. The Kamchatka Peninsula has really kicked in. There are now 5 active eruptions going on. So Russia has a number of there, and you know that we've had some significant earthquakes from that region. We just had another fairly significant earthquake in that area, so it's quite wiggly and wobbly. Kuril Islands has 1. Japan has typically 2, or actually this time Japan has 4 erupting, and the Philippines actually has 2 going on. So again, as I said, it is the term eruption is sort of a bit vague in terms of what one means, and when you see a list, you have to kind of decide what they're talking about. But it wouldn't be a proper nerd festival if it wasn't for an XKCD comic. And this is the mantle model, according to XKCD.
I saw this one in the wild, and it made me laugh really hard.
Every feature of Earth's surface that we have hard time explaining. Hypothesized mantle plumes. So I guess so people hear that eruptions, volcanoes are very common. We live on a very wiggly wobbly Earth, but a question to ask is, why do volcanoes erupt? What causes a volcano to actually erupt, and why are they erupting? What is this stuff?
So my understanding, this is from a couple undergrad classes in geophysics, right?
Landon, do you want to come back while she explains?
Sure.
I mean, you can say no.
So let me give the dumber answer. And then
the simple answer.
I'll give you the simple answer. Fundamentally, the simple answer is going to be pressure buildup. There are going to be some processes that will melt mantle material, and there are several processes by which you can melt the mantle. Just a reminder to everybody, despite what you may think, if you were able to take your shovel and dig down and look at the mantle, it would be a solid, not a liquid, right? It does convect over geologic time scales, right? But if we were to go look at it, it's a solid. So you have to do extra stuff to it to make it melt. And when that melts, you kind of have a chamber. Inside of that is the melted, molten mantle material. Say that 5 times fast. Melted, molten mantle material.
Melted, molten mantle?
Maddie says melted mantle, molten material. Yeah.
Yeah. And that is a like liquid in a solid chamber, right? And that think about it. If you take listen, put a Mentos in your Coke and screw the lid on and see what happens, right? That's kind of what's going on,
Keep
right?
pissing off your wife over and over and over again. You'll figure it out.
Yeah, you're building pressure inside of a mostly sealed rock container. And that has to release somewhere. And it's a lot easier to, so you're going to break out of that chamber where the rock sealing it up is the weakest. That is at the crust, not down towards the core, right? Like that's going to erupt open. And so that can be big and catastrophic, right? If we think like Mount St. Helens, right? Or that can be calmer, right? But that liquid and the built-up gases has to get out somewhere. And then depending on how much pressure or if it kind of gets stuck in some way, that's going to determine how vigorous the eruption is. How'd I do, Landon? How'd I do?
I think it's very good. So let's add some things to that. So magma, essentially, you think of it as, again, simplified terms, is essentially rock that's in a liquid or plastic-ish form, right? In form, and but people realize it's liquid. It has mass. It wants to sink, and if gravity were doing its uttermost thing, it would go down. But
uppity versus droppity.
And one of the mechanisms for going up, of several, is gases coming out of solution. Down deep, you have high pressure, and gases can be compressed to become liquid or even solid if you have extreme pressures. But when the material is moved up for various processes, it can go closer to the surface where pressure drops. And it's possible then for that gas that may be in liquid form to boil. Basically, it pops a bubble. And that bubble is going to give the magma loft, right? You're talking about pressure, right? And so you have gases coming out of solution that, bubbles popping like you see in your can of soda, and you see bubbles, carbon dioxide bubbles forming, coming out of solution and coming up. That is perhaps a fundamental thing. And so when we look at a volcanic vent, one of the things we're very interested in is what kind of gases are coming out. Because that tells you what, from that point, we see this gas coming out, it boils at this pressure, so it is probably boiling down at this depth. And then we take signals like seismic and listen to what we call harmonic pressures. Essentially, it's a sort of continuous rumbling of bubbles popping in and out. And by the way, when the gas bubble pops, there's additional pressure to push it back, so it doesn't just pop and stay and rise. They go back into losing it because you've got pressures and currents going on. So harmonic tremors will hear basically that the listening to the bubbling going on inside. But again, if there's enough pressure, it gets towards the surface. As it gets towards the surface, pressure drops. More gases go from liquid. More material goes from liquid to gas. It gives it loft. Eventually, breaks through the surface, and then the magma reaches the surface, and we call it lava. Now, one of the interesting things you see is that the volcanoes tend to, and on Earth, tend to be along plate boundaries.
Yeah.
And one of the things that is very significant in causing stuff to rise is forcing water down into the depth. Do you mind to talk about that?
Yeah.
Role of water in eruption.
I know. Here's what I know. I know that introducing ocean water into the mantle, it can be one of the things that triggers a chemical reaction that's going to start liquefying some of the that can start to liquefy some of the mantle. It has been a minute since I could recite the exact like chemical reaction that's going on. But that's also going to release some like gases as that happens. Um, so despite what oh my gosh, what there's some young earth creationist folks who think that what happens when you drag water under into the mantle is that it's like primarily what it does is like cool. And I'm like, there's so many other
No.
things that are going on that are more important than that. So that's
Water, the
one of the
universal solvent, gets into lots of things and lubes up and causes chemical reactions and so forth. There's lots of things. And also remember, you have time and pressure. So things that are even subtle become significant.
yes.
So
It's the straw that breaks the camel's back, right? It can go up, the pressure goes up, goes up, goes up, goes up, and it can only, all it needs is a little bit to.
But my other fun fact I know about this process is that this is one of the best ways to remove carbon dioxide from the ocean, because when you get that subduction and you bring the ocean down, the CO2 comes out, and that's how you get. Is the rock called cetraline? It's the green rock with the white calcium carbonate streaks that go through it. That's in all of the buildings because it looks cool. It's a great way to remove CO2 from the ocean, and therefore a great way to
posting CO2 down into the mantle is also a really good spot. And we are sort of fortunate because it's one of the ways that geology modifies the climate. Or has actively engaged in the climate process. I should maybe a better way to say. Also, again with volcanoes, so we have these spots where there's weak spots where usually there are magma chambers, right? So a volcano is really just one magma chamber. Typically, you have like a double boiler or multiple boilers, and there's a weak spot on top where essentially there's an energy flow coming out, where again, if stuff boils sufficiently and there's weak cracks, it can cause a surface event that colloquially is known as an eruption. The volcanoes, in terms of danger, because we also talk when Maanyaa's around, we talk about safety, is that volcanoes are typically most dangerous when they fall in on themselves, implode, not go bang, explode. It's not like a balloon popping where it is violating, splattering stuff. It's usually a case where the volcano collapses in on itself. Mount St. Helens was a collapse. There was an explosion out the side which weakened the base that caused the central plug to fall into the magma chamber and splash it out.
I mean, you would have a problem with the balloon analogy anyway, because it can't explode in all directions the way a balloon tends to do, because there's too much pressure coming from other places and other sides blocking it from going those other directions. So it forces the energy generally in specific directions.
Yeah, and so that's a very good point there, Chesh. And
thanks.
A better analogy.
Listen, listen. I'm just here to let the smart people talk. I'm simply a facilitator at the moment.
But anyway, and volcanoes like we have out in Hawaii are also particularly because they are because of where they are. We've got this plume, this sort of hot spot coming up near the Big Island. And that's an energy flow and a conduit which causes eruptions to occur. Kilauea being one of the most active volcanoes, has got a pretty good channel coming up, and we'll see from the earthquakes where it's headed. Mauna Loa tends to be also quite active. It tends to have eruptions on the order of like every 20 years or so. But when it erupts, it puts out enormous volume. The volume that Mauna Loa does an eruption is just staggering. Mololai also on the Big Island is a little active. But Mauna Kea is considered dormant. And part of that dormancy is the fact that there is no longer a significant net inflow of energy into Mauna Kea's magma chamber. It's in the process of actually cooling and will, when we call it extinct, basically freeze over. When volcanic hell freezes over, we put the volcano as extinct. Although when it's going from active to dormant and the magma chamber begins to contract, there are pressures in the freezing which causes little outgases. And so you'll see in a volcano that's considered mature, little cinder cones start popping up, basically zits pop, right? And it takes a while for that phase to die down before it becomes extinct. But the Hawaiian volcanoes are particularly nice because they are relatively gentle. They tend to not be cranky, although they have been cranky a couple of times in historic history. And I must say,
as opposed to non-historic history.
Yeah, you're right. Fair enough. But I mean,
I'm hilarious.
1790, when there was a catastrophic collapse at the caldera that actually changed the Hawaiian political landscape and allowed Kamehameha to become king of all the islands. There was a 1926 violent eruption that occurred, and then there was a thing in 2008 where the summit collapsed. And again, I remember watching, because I was a part of the group, watching the lava lake all of a sudden drop, and we watched it drop a couple hundred meters. By that time, we said, "This is bad. Something's happening. We're getting out of here." Right? And in fact, but Madam Pele, being a gentle volcano, it collapsed. It lost about a cubic kilometer of volume. It did it over about a month, and was rather gentle about it, right? As opposed to a Mazama type collapse with Crater Lake and it creates it. So let's look to see. But anyway, other comments, Maddie or Cheshire, regarding what makes a volcano or why they do it? There's a lots of reasons, but we're taking sort of the high level.
Is there much? I have a question about if there's any like tectonic factor, like plates shifting around that have any effect on like the creation of a volcano, maybe in its early stages.
Definitely. So like just think about like those subduction zones, right? So that is where a oceanic plate is going to go under a continental plate. And so that type of region is kind of a good way to start to form those magma chambers. So that's why that's one of the reasons you see like the Ring of Fire, right? Because that's very tectonically active. My kind of simple way of thinking about it is places where if you think about it as like places where we have edges of tectonic plates, if think about as those are the weakest points in Earth's crust, so that's going to be a place where it's easier for things to sort of release that way. That's going to be a path of least resistance, and so not impossible to have some sort of volcanic activity going on, not like directly near a tectonic plate, but it's going to be definitely easiest to have.
And of course, the Hawaiian chain out in the middle of the Pacific Ocean is one of those exceptions.
It's one of those exceptions.
And so there are. I was just thinking that there are common reasons why volcanoes erupt, but there's other reasons, and the notion of what's the Pacific hotspot and why is it where it is a area of research. We don't know everything, and that's why we have scientists to try to figure out and study.
We have a couple questions from the chat if we want to cover those now, if we're going to move from this into our Pele coverage. So Smitty asked, can we put nuclear waste down into the mantle too? It seems like the answer is theoretically yes, we could do that if.
Yeah, I mean, so the answer is, could you put nuclear waste down there? Yes, it's physically possible for you to try. Of course, it would sit in a shelf thing for a while, get buried, and take a long time for it to get to any sort of depth. It also, the period of time where it goes down and then it doesn't come up, depending on your half-life, may or not be a happy thing.
So
Yeah.
we can't. You're suggesting that it's not necessarily a good idea to build the equivalent of a bullet train for nuclear waste into the core of the planet.
I would be worried more about the containers breaking open while waiting to get into the mantle.
As it's like rocketing straight down.
Yeah, so when we talk about like a subduction zone, right, where we're transporting water into the mantle, we're not talking we're talking about like geologic time, right? We're not talking about timescales of human lifetimes or the length of time the field of meteorology has been around, which is like so these types of transport processes we're talking about are on the like tens of thousands of years is short, right?
Yes.
That's the type of timescales. And so in 10,000 years, any man-made nuclear waste is going to be pretty chill to handle by that point. And so it would be safer, right, frankly, to just put them in a very geologically stable location.
And then ignore it until we go away.
Yeah, and then
remember,
ignore it. Yeah.
Uranium and thorium are very common elements in Earth, right? The Earth has lots of it. If our model of how the Earth formed was reasonably correct, when the collision between the Earth and the impactor occurred and things vaporized, one of the things that happened is a lot of the heavier materials sunk towards the center. So we got a core region or internal region which was a bit denser in uranium than would otherwise be. So the result is that we have a planet that has radioactivity towards the center, generally,
right?
that a bit more than what's on the surface. And that's believed one of the processes that's driving convection in the mantle, right? Now this will eventually stop. Models suggest, because that continents break up and come back together, right? It's kind of this. Their continents are floating around and they break up and join back together. We think that the band will rejoin. The Blues Brothers will rejoin one more time in a post Pangea. Has enough action that'll combine once, break up, and then sort of stop. We don't think we're gonna have two cycles. So when that occurs, assuming that the hotspot in Hawaii is still active, then we will get our own Olympus Mons, right? We'll get a thing where we'll get a volcano which will go up above the atmosphere, the stratosphere, right? In a big way, and we will overtake Mars as having the biggest volcano on the surface.
And then the people living on Mercury or Venus by then will be looking at Earth being like, was there any life ever on this planet? We got a couple other questions. Okay. Rodent, no last name, asked.
Sure.
The recent Tonga Island eruption was a collapse that caused seawater to hit magma and flash in a boil to explosion. Is that correct?
Yes.
Then that answered the question. That was mostly my question. I was like, was that a collapse? I don't know.
Yeah, it was collapse, and it was a spectacular thing. Now, one of the things about that eruption was that the seawater, we had a couple hundred meters of seawater over the top of the collapse into the magma chamber, and the result was the gases that would normally come out and have shot into the atmosphere, creating aerosols and temporarily impacting climate, we didn't get as much sulfur stuff up into the atmosphere. Even when we looked at later on the lunar eclipse that followed, the lunar eclipse wasn't dark because there wasn't lots of dust in the stratosphere from that eruption. The ocean sort of put a little bit of a blanket on the gases that formed and the particles formed. It did shoot up there. I mean, it was a big, very significant atmospheric plume, but not as much as it had been above the ocean. And of course, one of the things is that meteorologists recorded the shockwave. My weather station, I have a calibrated weather station as part of the NOAA set, and we saw the shockwave come from Tonga, and then we saw the shockwave that went around the world the other way hit, and then we saw the shockwave again going, because that first one that went around again. So basically, when you get a big boom, they go around the Earth, round and round and round. It kept going, but by the time the fourth one was there, we were actually having a weather system where the actual normal atmospheric stuff swamped the signal, and we lost.
That's cool.
The echo.
That's really cool.
Smitty was also asking, wasn't Toba eruption an example of an entire volcano exploding? Toba eruption causing a genetic bottleneck in modern humans.
That was one of the big BEI-8 events, fairly significant. And again, that was a case where the mountain had erupted so much around the side that the top collapsed in. It did a Maanyaa. Right? Maanyaa is kind of the quintessential mountain on the scale of let's say a Mount Rainier that had lots of eruption around the side. The magma chamber was sort of evacuated by side eruptions, and the top fell in, and at that point it went boom. But those are examples of the big things. So even something like these so-called super volcanoes, which is another media term promoted by the History Channel, or what used to be called the History.
Oh, those guys.
Those guys.
For a area like Yellowstone or one of the other supervolcanoes to do its thing, it'll first have to fill the magma will have to basically create a bubble, and then you have to have lots of eruptions, and then the surface will weaken and then collapse, and then you get your fairly significant ash event. But it will take some time. So you will know by having probably thousands of years of volcanic eruptions in Yellowstone before the magma chamber underneath the Yellowstone basin collapses again.
We're going to have to do a mini-series at some point, or maybe a bigger series where I just force people who do science to watch the History Channel.
I am happy to say that the History Channel doesn't want to talk to me because I wouldn't give them a soundbite about how deadly a volcano could be.
Sounds like you don't want to talk to them either.
I kept using sentences where they couldn't even, unless they word spliced.
Ooh, yeah, that would have been dirty.
Because I don't give them what they want.
All right, so shall we go into our Pele tracking?
Yes, please.
I also just wanted to point out, as a child, I was like, when you're a kid and you have no concept of time, and you became like, I was deeply worried about like how much time do we have before the Yellowstone super volcano goes off, and like how much time do we have before the heat death of the universe, right? Like I was just like, but it's gonna end someday, and just
yeah. So yeah, don't worry about Yellowstone. By the way, I want to point out as well the USGS program. This particular link, I will put this link in our chat. They have a number of very nice articles that your taxpayer dollars are doing. I put this into our vMix link. And I want to point out in this set of articles, for example, there's a really nice article about Clear Lake volcanic field, and has some interesting information about Clear Lake and what happened and histories and so forth. We know about that thing there in California. There's another afternoon on there giving insights into Mount Maanyaa, that's Crater Lake in Oregon. It collapsed and what happened afterwards. It's quite fascinating. And then there was an interesting report about the arrest and eruption of Maanyaa in 2022. So I would
link is
encourage
now
you to
in the
go
chat.
look at those things there. But we then, one of the things we talk about is that Hawaii, in particular, Kilauea, Maanyaa, Hawaii, are probably the most heavily instrumented volcanoes on the planet. And we go over some of the data we get from it, even though they also surprise us. So
heavily instrumented means that they've got things that are measuring other things. Equipment.
Yes, and they have like one of Chesh's favorites. They got tilt meters, and
I like the tilt meters. They wiggle.
GPS tracking motion. They have gas sniffers and other things like that. Lots of data comes out of these sort of things. And this was in the morning, what happened. And in the morning we had the beginning of the 33rd episode, right? Kilauea started erupting on Christmas Eve of 2024. So
do you mind zooming that in a little bit for us, please?
2024. Okay. Sorry?
Do you mind zooming that in for us a little bit, please?
Okay.
And
so this is a case where and we've had 33 events. So Kilauea has entered into this episodic eruption rather than just having this continuous flow. They have a fountaining that's occurring at the summit inside Huli Ma'u, which is the central sort of pit of Kilauea. And we had this morning, the 33rd event started. It had an initial height of around 210 to 240 meters. That's about 700-800 feet. And then went down about 100 meters. Unfortunately, it stopped. So we'll have some pictures there, but it was definitely going there. During that time, the sulfur dioxide emission, one of the common things that come out of volcanoes, was exceeding around 50,000 tons per day. So we had lots and lots of that. Now, I think I'll say 50,000 tons is a lot, but it is not going to have a measurable change on Earth's overall climate. And nevertheless, when Kilauea get unrest, in a period of unrest, so it's not erupting, unrest, we begin to see elevated SO2 things coming out of vents. So when it's not erupting, you might be lucky to measure 50 tons per day. And when it's under unrest, you start seeing things around 1,000 tons per day. And then when it goes off, of course, there's lots of gas coming out. So one of the tells that Pele is up to something comes from the fact of gases coming out. But not only is SO2, which is one of the common gases, but you begin to try to sniff other gases to determine what's boiling.
Hey, listen, you better be careful about sniffing gases, all right? Don't give people the wrong idea. You don't need any Dutch ovens going on here.
Yes. Also, tilt meters there. But anyway, this is a notice about the beginning of that 33rd eruption. Deformation, they say tilt meters. This is measured in microradians. And a microradian is if you took a 1 kilometer bar and you raised it 1 millimeter. That is, you took a 1 kilometer bar and you stuck a dime on one end. It tilts a little bit. That's 1 microradian, really tiny tilts. And when we look over the past month, we see several events. We see these inflation-deflation cycles. Well, this thing that happened just right now, it was the beginning of episode 33. Here is episode 32. Here's episode 31. Now, this green line is out at another spot farther in the east rift zone. So we're paying attention to the sort of the blue line. And we can see also, we see this little blip here. There was a big earthquake in Kamchatka, and those waves came through the earth and shook Pele. And that little bit of that pressure vibration can cause gas to come out of solution and bubble a little bit more jittery. Just like if you took a can of Coke and just shook it a little bit, you get a little bit more fizzy at that space. So we can see earthquakes around the world that give a little bit of a zip to the thing, but not necessarily to cause it to do something major. And so we can see over the past 3 months, we can see these episodes, right, where it builds up to a point And then when it starts dropping, this is when the eruption begins. And eruption continues, the actual eruption of lava coming out, and when it bottoms out, it's lost its loft. And it will go back to building up pressure again. So we can see these episodes going on for the last 3 months. Any questions so far on this? This was that relative size. There was that big magnitude 8 quake in the contractile region. That's what that little bit was about. Questions so far?
I just wanted to point out for scale for folks, what is that 50,000 tons of sulfur dioxide a day mean? If we want to think about the eruption that caused the year without a summer, right? That one released like 58 million tons. And so, right,
Yes.
so to get us to, so that's 1,000-fold more than you're getting out of here, just for a sense of scale.
Yes, very good. Very good point.
We usually use washing machines as our preferred method of scale.
I don't know how to scale SO2, tons of SO2 in the atmosphere to number of washing machines.
Wait.
I don't know how to.
Because washing machine is roughly a cubic meter. So that you might say, well, that's, in terms of pints. You can also convert it to megapints, another thing.
Megapints is the other one we use, yeah.
Oh, okay. Man, I thought it was just Americans that would use any system but metric.
That is why we do this.
Oh, you have too many Americans in the audience.
Yes. You will hear me using radians and meters and so forth, and I'll translate it for those that are metrically challenged.
Okay.
So another area is
cross is that? I'm about 7 hamburgers tall.
We use precision GPSs in spots and measure distance. So this particular graph is showing you the distance across the Kilauea caldera. These things are about 3 kilometers apart, and we look at the distance change. And so here we're seeing a scale where each line is around 5 centimeters. It's about roughly 2 inches for those that are into inchworms. And what we see here is that the mountain expands and contracts. When there's an eruption, it drops, right? So think about the pressure builds up, and it's like a balloon or drum head expands, it tightens, and the result is that the 2 spots move away. When the eruption begins, it immediately contracts, right? So what you see on the drop is a result of an eruption. We can see these episodic eruptions occurring. There was we look over the past 5 years, we can see our current wiggly stuff of episodic stuff, but there's an eruption here. So GPS gives you had an eruption. Volcanic gases increasing will suggest you might get an eruption, and tilt meters will respond when pressure comes up. But that's magma moving, because we also have seen, and in this show, where we see tilt meters tilting and then it doesn't do anything. So just the fact that it tilts, magma's moving, doesn't mean it comes out on the surface. So that's another one of the meters. We have lots of maps here. So this was, we had our last, it is monthly thing. So since the last time, several of the eruptions occur. We actually had 3 episodes. And here we see, this is the Halimamau caldera now, and the lava pit. And this is the main caldera at the summit of Kilauea. And the vents occur around here where most of the eruptions are occurring, and it pours out into this area. Now, this thing is called the drop down block. And we'll see another get another picture here. This down block was where the summit collapsed. This used to be level, but if you go over here, here's the summit of Kilauea, and in 2018, at the end of that 35.5-year eruption, so we had a 35.5-year continuous eruption out of Kilauea, and then magma moved all the way out to the end. It came out about a kilometer of lava came out in a period of a couple of months. There's a huge flows out the end of the island. The result was the summit was empty, right? It largely emptied a magma chamber, and the rock on top couldn't hold up, and it collapsed. And it collapsed with a series of magnitude 5 earthquakes about every 20 hours. It was almost like clockwork. And it was really fun there because you could almost set to say, we're about ready to have our magnitude 5 quake, and it would rumble, and the thing would sort of shake and sort of settle a bit. It was like nice if you're into earthquakes, you could do experiments predicting, because you've got these magnitude 5 earthquakes coming. There was a fun time. But nevertheless, it didn't collapse in one big thing. It collapsed in a whole series of these nice little steps over a period of about 40 days. The result was that the bottom of the pit was about halfway down the sea level. Right, it dropped significantly. There was something almost on the order of around 900 meters at the bottom. Right, it really fell down. It's filled in significantly since that 2018 time. And so the events here, again, here is a matter of a kilometer in size. The events that we see, eruptions are occurring here and flowing into this pit. So it essentially, the lava smooshes around in here, doesn't really bother anyone, and it can come to the area in Maanyaa overlooks and watch it occur.
I believe a little bit further down, it will answer Maanyaa's question in the chat, is how much lava is in the crater now.
Here is let's look at this September 12th map. And here we talk about the statistics. This is through episode 32, so we don't have the last episode 33 that just ended. So the average thickness is 972 meters. So we have a very deep lake. Since the beginning of this eruption phase, so it started Christmas Eve of 2024, we've added 55 meters. So we have over 374 hectares, or that's at 924 acres. And the total volume that's come out since Christmas Eve is almost 154 million cubic meters. That's 154 million washing machines, or around 41 billion gallons since Christmas Eve. That's a lot.
That's a lot.
That is a
You prepared me for the washing machines, and I wasn't prepared.
That's a lot of fish. There's gonna be like 4 people in the chat that get that reference.
So if you think about in terms of pint, because if there's 8 pints in a gallon, and we have 40 billion gallons, we have essentially 8 times 4, 320 billion pints. So we have roughly 320,000 megapints.
320,000 megapints.
Oh, goodness.
Or 320,000 drinking engagements with Johnny Depp.
Alleged drinking engagements with Johnny Depp.
Well, according to
Amber Heard's lawyer,
they wouldn't lie.
A megapint.
Now, I will point out, we'll leave it there. We'll also see this. We had a little bit of a fissure open up in here, where on episode 30, that was 3 episodes ago, we had a little bit of lava coming in. Mostly it's been coming on this spot. So let's look at more stuff here. I'll point out, by the way, the crater floor elevation had a jump because, again, we had a lot of lava coming out, so we added some material. If we look at the earthquakes, of course, we have earthquakes up the summit where the eruption occurs. We also have, and the blue is showing you depth, right? So we have a series of quakes that is to the southwest at around 30 kilometer depth. And this, we believe, represents the mantle plume, the hotspot coming up. And there is an action occurring where something is boiling that gives it an initial loft. And this magma heads towards Kilauea, Mauna Loa, Kololai, and of course, the volcano off of the coast. So we see Earth deep at 30 kilometer level because this, we believe, is part of the sign of the mantle plume. And it continues to do stuff. Although we had a big earthquake here in 40 kilometers deep. So we do get quakes there, but they tend to be fairly small and continuous. And then we have other things in the top. Again, crater floor elevation. As each time you get an eruption, of course, there's expansion and contraction because of the magma pressure. And then we stick lava on top, and now the floor elevates. So we see the jump, jump, jump. Here's episode 32 level, 31 level, 3 level, and we can see it went from around 922 to around 925, and now it's probably up to about 992 to 994 to 995. It'll probably be up to 996. And remember, the scale we're talking about, we have a case where it's a couple kilometers across, adding a couple meters onto it. A lot of lava comes out. So if we look further at what's going on here, we have pictures. So this was the picture that I took this morning. This is the video camera image from V1 Cam of the episode 33, and we see that the vent is actually the plume is actually getting more vertical. So Maddie, in the 20 to 25 episodes, we had mostly vertical, very tight hole that resulted in lava plumes that were on the order of like 370, 380 meters. So big, tall fountains. Some of the tallest, the tallest in recorded history in the caldera. There was a taller one to the side in 1959, but it approaches that. So in feet, you're talking about things around 1,300 feet. And then the events started going to the side, and so they started going lateral. They weren't high, but they were certainly voluminous. This one returned to where we had a little bit of verticality as well. So that was a picture from this morning. If I refresh it, it'll show you basically that nothing's going on at the moment. But this is also another one from this other side there.
What a color.
I helped actually install these cameras. So thank you very much. On the summit, you can see where the buildup has been occurring from these fountaining. And again, give you in terms of height, this is probably around, I would say now around 200 meters or so from here to here in scale. S2 cam, we got another one here. Now we towards the end, it has sort of this 45-degree angle, so it wasn't completely out straight, but it wasn't up the top. And here you can see the ash plume that is the ash piles that are coming from these events over these 33 episodes of stuff. Here's another one, V3 cam, showing them the sound volcanoes make when they're erupting is incredible, and it's something that you just have to be there to hear because your stereo can't really give justice to a mountain-sized subwoofer doing its thing. And if you have a spectral analyzer, you can find very interesting resonance around 7 hertz and 3 hertz and around 14 hertz. There's these resonance frequencies that occur from these eruptions that are quite interesting, and you can feel in your chest if you're near it some of the overtones of it. And yes, we use sonograms to look at the sound of a chill coming out. Here's another one showing you the caldera. So this is the down drop block, and you can see the extent of lava coming out. The lava going here, all the way out to here. Now, most people don't recognize lava when they see it. They only see the red stuff is only when you've got hot material that's actually in motion, right? The atmosphere is cold, and so as soon as this lava comes in contact with the atmosphere, it begins to freeze unless it's moving
all
rapidly.
That darker stuff is all still lava.
Yeah, this is very toasty in that area. Now, we also look at air quality stuff, and there was no real air events. But again, given the way the trade winds go, the gas coming out is basically going to the south, to the southwest.
So it is away from the current population.
Yeah. So
have you guys?
Go ahead.
I was gonna ask, have you guys ever talked about the pyrocumulonimbus clouds?
Yes, we have some pictures coming up.
Okay.
So
we haven't, but we're about to.
Yeah, they're one of my favorite things.
So they're really cool. In fact, so here we're looking again at the Kilauea caldera, and this is looking at the down drop block. This over here is this is Mauna Loa. This is the big island, the big mountain, right? This is the largest mountain. Mauna Kea is over here. So we're seeing enormous distances, but we're going to focus on this. Is a movie that starts in December 20th, and you're going to watch over time the caldera fill up, right? So here is the movie, and you see the eruption, stop, eruption. Look at lava going whoosh, 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 more layers, thicker, big spots, small spots, big jumps, small jumps, but again, more and more. We're now into March, we're into April, we're into May, June, July, August, and there it is. So you can see this. You can see this action occurring in it filling up. That's the 320,000 megapines or 100 and some odd million cubic washing machines. Understand, you should appreciate that geologists normally see snapshots frozen geologic time. To see something like this happen in a human, let alone TikTok way, is amazing. It really is a extraordinary event.
You don't have to work backwards. We're actually just walking through it.
Yeah. So I want to point out that that's one of the real joys of being at the Volcano Observatory, is that, and seeing this mountain eruptions, you can see the island changing size, right? As you visit back. Here's another thing showing you the difference between this is what it is. This is what it was, right? So in 2024, December 20th. So this is like 3 days before it began its current set of eruptions. So this is pre-episode 1, right? And then this is now. So that's what it's done. That's what it's done since December. From there, we had a couple of dribbles to there. Significant amount of stuff. Again, these eruptions are putting on enormous amounts of material.
So, Landon, I know you had some pictures specifically that you want to show Maddie here. And I know she's got a little bit of a limited amount of time, so we should probably get through those.
Yeah, I'm going to show you there. There's a vent there. There's some of 31.
That looks like a fan.
Yeah.
Some of the stuff on the side. So here is one of those plumes where you can see the atmospheric effect of the output. So you got a lot of heat being generated to creating these cloud systems. Now carrying in there is ash, and so you see back here a big this is a big ash pile that's been formed. So this is one of the things you see during an active eruption.
One of the important points for meteorologically there is that one, smoke is pretty wet. So you're bringing in, not only getting a heat source that has that's going to induce a rising motion, you're also introducing additional moisture locally, and ash and lots of little particles are really good. So guys, it's hard to make a cloud droplet.
Yes.
When you
it really water would rather just don't want to congregate. They want something to join.
It needs a nucleus of something for it to grab onto, and then it grows around that. Turns out all the gunk you get out of a volcano is really good for that. So it's really good, and it's also highly there's definitely some extra chemistry going on for electrical properties. So it's easier to make light in these types of storms.
Lightning in there, and you're in a humid spot. So the air has got all this moisture hanging around, and then you get a spot there. I'll shoot. There's a couple of better pictures there that they gave me on. Here's another one of the
Okay.
31 plume. Another
Nice.
really showing you the lava trail coming out of it. This is 31.
That's really stunning.
You can see the extent of this stuff. Again, this happens in a matter of hours, right? Of this
Wow.
flow that sits inside this pit. Really cool stuff there. Here is also the case again. The big island, the big mountain. This is not a hill. This is the largest mountain on Earth, and I mentioned saying that answering scientists say, well, you got an answering science shorter this.
Oh, nice.
That's a mushroom
See,
cloud.
That's a helicopter right there, right? This is again human.
That's huge.
Creation.
This is
and
pyrocumulus.
This cloud is probably around 2 kilometers in diameter. There. Here's another one.
So if you go 100 kilometers an hour, it would take you 2 hours to go across the cloud.
No, this is 2 kilometers in size. If you're going 100 hour, it would be
1 kilometer.
1/50th an hour.
Yeah, 100 kilometers an hour. Sorry, 1 kilometer an hour.
Yeah,
that'd be really slow.
Yeah. So this is from the volcano house. You can see again these plumes coming out there from this set. Here's another example showing you. So we had a storm system coming in here, and an actual eruption, out here with that helicopter scale. And again, you can see that. So even though we had a front coming in, it was exaggerating the droplet formation underneath with stuff. So yeah, they said, "Oh yeah, sure these," because she thinks these. They think these. Cool.
I love it.
I get you these pictures. I get you these pictures, but look at this cumulonimbus that's formed above the eruption. This is a fairly tall plume coming from this source.
How far away is the house from the volcano?
We're at about 3.5 kilometers to 4 kilometers from there. I would say around 3.5 kilometers or so. So give me a scale. But anyway, I'll send you those pictures because they said she'll probably like this.
I love it. Yeah, this is great.
Here is that little. I point out that little thing that happened in episode 30 with that dike. This was where it we had a little bit of a crack that came out here. So now we're at episode 32, and again we have a lot of verticality, lots of ash there. Near this area, and you're underneath that plume, you basically want to use gas mask because silicosis is a real thing. But look at the ash deposits from this set around
It's
here.
deep,
really deep, dense stuff. Very unstable.
And we can use this kind of information because when you look at something from a geological scale and you look at how it's been crushed and what those layers are, you can get even a little bit better idea of what you're looking at if you compare it to what we now see in how much is dropping.
Yeah. Safety-wise, you don't want to get, because there's lots of silicates and glass stuff there in the air. You don't want to be breathing
glass
stuff when you're sort of down. So, but I'll show you this particular thing showing you the come in safety things. They are going to do measurements walking in. This was the current outflow, real-time outflow from this set, and they're taking measurements. You can see from lots of, again, this is an enormous scale of material. I was impressed on the scale of just how much stuff is coming out.
Wow.
And the sound is just gorgeous.
Yeah, you weren't kidding when you said really you had a bunch of volcano porn today.
This is good.
Right, you could see this stuff, these giant boulder blobs, liquid boulder blobs splashing in there. You get these fractal patterns of that river going. Lots and lots of material. Look at the material. This is sort of the bottom of that stuff. And of course, you take samples of stuff, paint buckets, and you reporting there and watching the stuff shoot out to the side. For this is 32. And of course, the atmospheric stuff occurring behind you near sunset. All right, so time to pack it up and bring the data there.
Whoa.
Night views as well.
That looks like where you could put Obi-Wan Kenobi and Anakin Skywalker in that, and you wouldn't tell the difference.
Yeah.
Except the scale, they would be little small blips on the side.
They'd be so tiny.
But you can see so a lot of material afterwards coming in. There's the vent afterwards, and you're collecting samples again, looking at what's coming out, the type of material, the gas coming out. I want to show you another one here again. These beautiful sort of rivers with the fractal patterns that come out from there. These flows are just good.
Mustafar at home.
So one of the there's some very simple things like just putting in a paint bucket out there and see what falls in.
Oh
to
yeah.
give you an idea of the ash flow. Again,
is that like a 5-gallon bucket?
Yeah. All stuff. And this is to be a road here. It's now under this since there's about 20 meters deep. The ash that's piled on the road behind this event is about 20 meters deep since the beginning of Christmas Eve.
That's a lot of ash.
Getting even close to it, right? And it blows downwind from the area. They closed the road for a reason.
Yeah, you think?
That. Yeah.
The last thing I want to show you is again what occurred from the recent eruption. This is where it gets started, where you can see the beginning of stuff, and you get the blooms, and then the whole thing takes off. So you see it's at 7 a.m., 8 a.m.
2 hours.
You see how the direction changed. 9 a.m. We're at 10. This little side vent went off at 11. Here we're at noon. Here is at 1, 2, 3, 4, 5 p.m.
Wow, that's 10 hours so far.
6 p.m. Sunset. 7 p.m.
12 hours.
8 p.m. and then we're kind of done.
So 11 hours.
So that's
13 hours of eruption time.
Yeah. So I'll undo my thing here, but that's the stop sharing.
I don't know if a snowplow would be very effective against all that ash and glass. I feel like it might just shred the inside of your snowblower.
Yeah, and it's a while that they used to have the rim going, the drive going around the rim. They stopped the Southwest because of the eruptions occurring. It'll eventually stop, right? Because it's not going to continue erupting. This pattern we're in episodic it's easy to assume it's going to always be erupting. Right?
Maybe I'm thinking of a snow blower and not like a plow, like just like with a big shovel on the front of a truck. Yeah, probably fine.
Yeah, but it is the ash stuff is really silicon glass. It's shattered glass. It's a lot of stuff there. And
11 hours. Here, I think that's the requirement for maybe taking a visit to the doctor.
So when you have the blobs of lava shooting out high into the air, it trails behind. You get these long streamers, and those get to be really glass filaments, and so you have lots of sharp needles of glass. Don't fall down. Don't get them in your lungs. They will. Ooh.
There is one question from the chat that we should then use as our kind of jumping off to get out of here, because I know we're getting near the end of our.
We have to do the predictions though. But
we can't do our predictions today.
Predictions
we can't. We don't have Maanyaa today.
Well, we can at least comment on that.
Well, okay. You can make a prediction, but we don't know who won last time. We have to find out who won last time, next time, and who won this time.
So Maddie,
next time.
Part of the thing we do is we try to guess what will the volcano be doing next month.
Oh, okay.
So
we
get
then
your
laugh at
predictions
how
in.
bad our predictions are.
Well, I asked this question, which is Smitty
Okay,
asking,
please.
if I lived in Hawaii, could I get that close and drink a case of beer on the side of the volcano while I watched? So he's basically asking, how close
Yes.
can I be to watch the volcano?
So you can get very close. I will say that, for example, the overlook can put you less than a kilometer from the vent, and it's really obvious there. So you can get quite close. You can hear the sound of the eruption quite easily, and from a map perspective, I'm bringing up this thing here.
It also depends on how much PPE you want to wear.
Yeah.
That's true. Well, from the safe point of view, right? I'm looking at the overlook, and
how close can you be if you were naked?
You are about a kilometer and a half is the closest. Again, these are very safe spots. You're upwind. They monitor the gas in case the wind's
upwind or downwind.
Yeah.
Right.
You don't want to get ash in your beer, but it's okay to get beer on your ash.
There's also hiking trails to the south, but you kind of stop there. It's better to do the drive. Drive can get within a kilometer and a half. There's some really good views across the caldera. Very safe. And although sometimes it gets crowded when it actually is venting there, but it still is. It's quite close. And there are lots of Indigenous First Nations people that come to pay their traditional respects to Pele, and it's quite kind of nice spot, especially at night when people bring offerings there. They leave the offering. You don't throw your offerings at Pele. That's considered rude. You bring from your village, wrapped in a tea leaf, objects that are important to your village and your people. A common thing is that child's baby tooth and someone's a bone of a cat that they adored that died, all these sort of things that are brought there. They also bring alcohol. Favorite drink is Seattle's Copperworks whiskey. And they also bring in medicinal herbal additives too.
You don't smash that like button. You touch it gently. You don't throw things at Pele. You gently offer them.
Yes, and the other thing is you share it with other people around you. So you have a group share. She gets the majority of the share, but you're showing Pele, we're partaking of this. Here's some for you as well, right? You share it with her, and throwing food at someone or other things is considered rude. So it's done in a respectful way.
Yeah, so there's not a whole ton of predictions in the chat as of right now. My prediction is going to be that the volcano is going to chill. It's going to stop. It's going to be done.
So I'll do the opposite. It's not going to be chill. It's going to stay the course.
All right, Maanyaa, you better write these down. I know you're in the side chat.
And I'm going to agree with Dr. Maddie. I think that we had 3 episodes this last month. I think depending on how the numbers are, I think we're going to have 2 to 3 episodes again. So Chesh is saying 0, which, at some point Chesh will be right because it will stop.
Someday Chesh is right. Landon 2025.
Somewhere it's going to stop erupting will be right. For 35 years, when Pele would go through eruption phases, they'll say, well, now the eruption is going to stop. Now, and for years and years and years, there are these geologists that were notorious for the number of times that they predicted the volcano was going to stop erupting next week, and were wrong. It's all going to do what it does. But I think, Maddie, you're right. I think that there is, when we saw that we had 2 or 3 episodes here, it kind of depends upon the phase stuff. Again, I think 2 or 3 is still the case.
I'm sorry, did you just say the phase stuff?
The phase of the episode, right?
PH. I heard like Fae, like FAE. It's like volcanoes are just phase shit.
Had the show been 12 hours earlier, we would have said 2. Now we just got to 3. So the question is, will the next month be 2 or 3 episodes? I think. But the other thing to think about as well is that the episodes, the volume of lava coming out in each episode is still significant, even though they are coming out more late. So it used to be that the volume used to be around, episodes used to be like every 6 days or so, 5 to 6 days, and the volume was short. Now, when you have an episode, there's much more volume coming out. It's just taking longer between.
Rodent says that Chesh could be right. She is a Harvard student now. Fuck you.
Nice.
And then Smitty says I have to drop out publicly because I have a reputation to maintain of dropping out of school.
Well, that is true. Well, people from MIT will excuse you for being a Harvard student, Josh.
Oh, okay, thanks.
Yeah.
If you know anything about MIT,
I don't.
They make
the thing is great, but Harvard is famous for its dropouts, and MIT is famous for its graduates.
Oh,
Yes.
That makes sense. That's why I'm at Harvard. That tracks.
But anyway, it's been very. I really appreciate the addition to the show there, and I'll forward on those atmospheric things because they were talking about saying that we're going to do this month, and I mentioned. Right, so I said, we got to give her this stuff. So yes, they had collected those things. So I'll send you those photos.
You'll have to come
And
another time when Maanyaa's here.
I need to come another time when I'm not quite so sleepy.
Yeah. Also, to be fair,
But
you've been very busy.
I've been very
That's the
busy,
show.
and I
Listen,
didn't know I was going to be this busy.
You are welcome to come anytime you would like, and you're welcome to come for any topic you would like. So,
Okay.
feel free.
And so Maanyaa, who's in the chat, recorded correctly 2 or 3 episodes before the next show. Correct.
Okay.
And Maddie agrees.
All right, that's our show for today, everybody. Let's get on out of here so Maddie can go to sleep, like the busy bee that she is. Thank you so much for joining us, everybody. You can find links to people's stuff down below, and I'll make sure to add Maddie's. It has been pinned in the chat, so make sure to like and subscribe and share, and go check out Our Favorite Universe with Landon, also linked down below. Thank you so much, everybody. Bye-bye.
Bye.
Bye.